Hi there. Okay, this video is going to be centered around the concept of the electric dipole. There won't be any math in this video. Yay. So the electric dipole is essentially a positive charge and a negative charge that both have equal values. This could have a value of, let's say, 4 microcoulombs positive and negative 4 microcoulombs. It doesn't really matter. The reason that the electric dipole is important is because it's something that is a simplified version of what occurs in nature all the time, and that's basically what we're going to kind of center this video around. The electric field surrounding a dipole can be determined in a similar way to how we did the multiple charge electric field video. You can create electric field lines from both mathematically, but here we can kind of see intuitively the effects of both of these. So if we were to select any point on this field around, or this space around these two charges, then we can identify the field that should result from the negative charge and the positive charge in an estimate. So we can create an arrow toward the negative charge here, and we know that that's going to be some field strength here close to the negative charge. So the field from this positive charge would of course be weaker because the positive charge, even though it's the same value, is farther away. And the field that results should be something like this. It's going to be away from the positive charge and much smaller than the larger arrow presented by the negative charge because the field from the negative charge is stronger. When we do a resultant vector, we get something that looks like this. Now, if we get rid of the component vectors, then we can see the resultant vector only, and I personally like to represent this not coming from the point that this arrow represents. I like to kind of balance the arrow on that point so that it represents it a little bit more visually to human eyes. So if we were to do this in every place around these two charges, then we would find a field that looks something like this. Notice again that this is represented by field lines leaving the positive charge and entering the negative charge. Field lines, again, always originate on positive charges and terminate on negative charges. In this case, we have just as many field lines leaving the positive charge as are entering the negative charge. This distribution is something that we actually see pretty frequently in nature, but it usually doesn't take on a point charge configuration. It's a little blurry. And the reason that this happens in nature so frequently is because, as you might imagine, when you charge objects, you have to take charge from one object and give it to a different object. And therefore, by separating a certain amount of charge off of one object, you've, by definition, placed it on a different object. And so it's very common in nature to remove 1 microcoulomb of electrons from an object and place it somewhere else, thereby leaving 2 opposite charges. Now, where I just used 1 microcoulomb as a random, sort of randomly chosen number. It doesn't have to be that amount. It's much more frequent to have picocoulombs and nanocoulombs. There are some cases where quite a bit of charge builds up in your daily life. Let's explore those now. So let's look at the case of zapping yourself on a doorknob. So we have a doorknob and a hand here. You're pretty familiar with this probably. And under normal conditions, if your hand approaches the doorknob, then there's no cause for anything unusual to happen. Let's not forget that doorknobs are filled with charge, as are all objects. It's just that they happen to have a neutral charge, and they're conductive. So here we represent some charge that's canceled out. Of course, it's not all the charge, but we're basically just representing the charge that already exists on this doorknob. Now, if the hand that approaches the doorknob is neutral, then you're not going to have a problem. If, on the other hand, you've rubbed your feet on the carpet and through triboelectric charging have managed to accumulate charge like we've talked about previously, human skin is actually not the best conductor, but it's conductive enough that it can carry that negative charge. So now that we've got this negative charge on our hand, it can migrate a little bit because, like I said, human skin has a little bit of conductivity. As we bring the skin close to the doorknob, you can expect that the negative charges on the doorknob are going to be repelled away from this excessive negative charge. As this occurs in a minor way, you're going to see a positive charge here on the tip of the doorknob that's going to begin attracting the negative charge on the finger. Now this is all occurring while a field is developing, something like this. Now, as the hand begins approaching the doorknob, we're going to see a gradual development of the field and a gradual accumulation of charge. This leaves electrons left over on the other side to cancel some of the excessive charge that built up in the doorway. This is the process of shocking your finger on a doorknob, and it explains it in terms of electric fields and in terms of the dipole. Another phenomenon that occurs with charge separation is very similar to the doorknob, but on a much larger scale, where clouds have a tendency to separate negative charge through mechanisms that are still being studied. But we know that this charge separates toward the bottom, so that negative charge builds up on the bottom of the cloud layers and actually in different atmospheric layers. But in particular, the ones that we're interested in are the ones that are closest to Earth. Now, Earth is like human skin in that it allows charge buildup. So if there are any metal objects or anything, this happens even more easily. But this charge buildup will occur like this, started with neutral atoms and the negative charge fleeting. The amount of charge that builds up is pretty significant, and so it doesn't take much for a small leading trail of negative charge to find its way to the ground and open up a weak pathway for the very strong electric field that is forming, like so. When this occurs, there's a discharge of electricity in much the same way that your finger discharges electricity onto doorknobs, except for, again, on a much larger scale. This small discharge that you can see occurs here actually opens up an avenue or a pathway for an even larger amount of charge. And of course, this is lightning. Okay, so hopefully this kind of demonstrates the idea behind charge motion and the idea behind the dipole, the electric dipole, and its importance in nature. This concludes the section on electric fields as strictly entities on their own, but our third section will be very heavily dependent upon electric fields because we'll begin studying electric field flux and something powerful called Gauss' law.